First, a programme for the course Technology and Change, 1750 to 1914. It's a film about the lead chamber process of making sulphuric acid. Shot in 1973, it features the last remaining sulphuric acid plant in the UK, which has since been demolished.
This is one of the most famous chemicals of all time. Even its formula is familiar to most people, H2SO4. It's important because it's so versatile. It can dissolve or corrode away most metals, and here it is merrily giving off hydrogen on reaction with zinc. By the same token, it goes for rust and can clean up iron surfaces before it attacks the iron. It can even expel other acids from their salts. This one is nitric acid. It has a ferocious avidity for water, as you can see. And it will even dehydrate a substance like sugar to form charcoal. Yet another role is as an oxidizing agent, even attacking copper, which is not affected by most simple acids. It can attack organic compounds in yet another way, by sulfonating them, from which we can obtain things like dyes and saccharin. Here, it's reacting in a complicated way, degrading organic substances which are being analyzed for nitrogen. The great German chemist Liebig once said that the commercial prosperity of a nation could be measured by the amount of sulphuric acid it consumed. And for most of the 19th century, sulphuric acid was made by one method in works like these. These are plans of a factory at Seaton Carew in the northeast of England, which was almost certainly the last in the world to use this method. In 1973, we were incredibly fortunate in being able to be the first and almost certainly the last people to film this process. It was a technique on which much of Britain's future greatness depended, the lead chamber process.
Here at Seaton Carew may be seen all the features that characterized the lead chamber process during its emergence in the 19th century. First, the great lead chambers in which the reactions took place, themselves a heritage from the 18th century, in fact. Then the furnaces outside the chambers in which the raw materials were burnt. And finally, the massive lead-covered towers that were to become such a conspicuous feature of the plant in its later days. Yet there was a time early in the 18th century when sulphuric acid was produced only on a minute scale. It was made by heating the vitriols, themselves prepared by weathering certain minerals. In this way, sulphuric acid became known as oil of vitriol. But because of the expense of the raw material, the product remained largely a chemical curiosity. All this was to change with the invention of a totally new method of manufacture. We can put it very simply like this. Water, the colorless gas sulfur dioxide, and the brown gas nitrogen dioxide react together to give sulphuric acid, H2SO4, the most famous formula on record, and one other product, a gas, nitric oxide. Fortunately, oxygen from the air converts the nitric oxide back to nitrogen dioxide, and so the process can go on. In this method, sulfur dioxide was formed by burning sulfur, formerly called brimstone, a substance which occurred in vast quantities in Sicily. In 1697, Lemery had described an experiment in which sulphur and saltpetre, two of the components of gunpowder, were heated together in a bell jar over water. The white fumes that are given off dissolve in the water to form a very dilute solution of sulphuric acid. In England, the first industrial application of Lemery's experiment seems to have been made by Joshua Ward in 1736. Known unkindly to posterity as the notorious quack, Ward presumably required the acid for his pharmaceutical concoctions. He employed glass vessels of about 60 gallons capacity. The new supply stimulated a new demand, although it was a demand which Ward's equipment was quite unable to fulfill. Sulphuric acid will pickle or clean away the corrosion from a metal surface. Despite Ward's attempts to keep his method of manufacture secret, sulphuric acid works began to spring up all over Britain in the neighbourhood of those industries concerned with the purification and cleaning of metals. Shortly afterwards, by mid-18th century, increasing demands for the acid were being made by another sector of industry, that concerned with textiles. Expansion of the textile industry had been held up by the time required for the traditional bleaching process. In this, the cloth had been treated with alkali and then to a prolonged exposure to sunlight. Finally, the alkali was neutralized by sour milk. But in 1756, Francis Holmes suggested replacing the milk by sulphuric acid, thus greatly accelerating the whole process. Later still, in the 1780s, the whole bleaching process was transformed by using the newly discovered element chlorine. The production of chlorine again involved the use of sulphuric acid as its first step. Nor was this all. There was a tremendous increase in demand due to the emergence of another great chemical industry, the alkali industry, described in another program. Throughout the 19th century, new markets for sulphuric acid continually opened up. 1842 saw the first patent for the use of sulphuric acid for making fertilizers. And from 1854, it was employed in the manufacture of alum, a chemical used as a mordant, something to help dyestuffs to adhere to fabrics. And so we have this major problem of a vastly increased demand. Given Ward's glass vessels, industry would soon have been starved of its vital sulphuric acid. They were so small, yet they could hardly have been bigger, for glass was both expensive and fragile. The problem of vessel construction was solved by John Roebuck in 1746. He made lead houses for his reaction, roughly 6 foot each way. And indeed the problem then became that of building lead chambers large enough to meet the increasing demand for sulphuric acid. It was quite one thing to build small lead houses, and quite another to construct vast chambers the size of a cathedral. Lead was, of course, a familiar metal, but it had never been employed on this scale before. Breakthrough is a term one should normally use with caution, but one certainly occurred with the realization that lead sheets can be joined together by autogenous soldering, that is, using molten lead itself in place of ordinary solder. Obviously, this requires a hot flame to melt the lead. Today, an oxyacetylene flame is used, but in the last century it involved a hydrogen blowpipe, which produced a hot flame by burning hydrogen gas in a jet of air. Air was pumped into the flame with a bellows pump, but hydrogen gas had to be specially generated by dropping acid from the top onto zinc in the bottom compartment and tapping off hydrogen through a valve system in the middle. This apparatus was known as the plumber's machine. By means of this simple contraption, lead sheets could be joined together on site to produce chambers of the huge capacity that were to become a common feature of sulphuric acid plants by the mid-19th century. Only with chambers of this size could sulphuric acid be produced on anything like the scale demanded by the new industries. We're now up aloft inside one of the housings of a set of lead chambers here at Seaton Carew. You'll notice we've come a long way since Roebuck's time. And these chambers are constructed on a scale far greater than he ever knew. Each of these is about 40,000 cubic feet capacity. But they're not the biggest that have ever been constructed. Some chambers 4 times that size have been made. Now, anybody who starts to build a lead chamber on this scale is inviting problems, because lead is a very unsuitable material in some ways, being both soft and also dense or heavy. It tends to sag under its own weight. And so it has to be supported on a wooden framework like this. It's made of pine wood, and it's kept a few inches away from the chamber itself. This is because the chamber is quite hot. It has to be circulated by cooling gases all the time. If this were not so, there'd be local overheating and a very greatly increased rate of corrosion inside. And so the lead chamber is supported by the wooden framework at a distance. These lead flaps are used to connect the two together. Now, on the other side of this walkway, there's another wooden framework. This one, also very substantial, holds the shutter boards, which are the most conspicuous feature of a lead chamber plant from outside. There was a case where this shuttering was not in position in Bolton many years ago, and the whole chamber collapsed at the gust of a particularly violent gale. Now, this chamber is working, but the next one in the series is not. It's under repair. So we're going to have a look at that now. This is the lead chamber that's under repair. It doesn't normally have a hole in it this size, but it does enable us to see some of the interesting things inside. We can see the thinness of the lead, about 1/4 of an inch thick, perhaps. The depth of acid at the bottom. That's about 1/3 of what it would normally be. But the most impressive thing is to see the enormous volume of the chamber and the great cavernous depths in which the reactions took place. Wherever there was the need for sulphuric acid, a plant was erected, because at the end of the 18th century the roads were so bad that it was quite impossible to transport the corrosive sulphuric acid for any great distance. There was another factor as well, and that was that in Roebuck's time there was a very considerable amount of successful industrial espionage by which these prized secrets were obtained by rivals and competitors. Some of the ideas seem simple enough to us now, but we must remember that this was the first time industry had really faced the problem of coping with large quantities of hot, corrosive, toxic gases. It was not until 1810 that the idea was put into effect of producing the gases in a furnace outside the chamber, and then leading them through a series of chambers until the chemical reaction was complete. This gave a continuous process, which meant that an efficient means of cooling the lead chambers from the effects of the hot gases had to be found. These problems were often solved by raising the chambers on wooden supports high above the ground, as can be seen at the sulphuric acid plant at Seaton Carew. On the roof of the chamber, the works manager, Mr. Eyre, told me of some of the problems of handling the hot gases. Why, for example, the roof is particularly vulnerable.
Well, it's supported entirely by these straps. All of these straps are burnt onto the lead sheet, wrapped round the timbers and nailed. We tend to get these cracks especially around the sides where most of the weight is. This chamber has been in use for about 15 years or more, and it's actually getting a bit beyond repair while it's in use.
Throughout the last 200 years, the lead chamber process has suffered many vicissitudes of fortune due to the changing nature of a third problem, that of the availability of raw materials. The traditional source had been the element sulphur, itself obtained from the volcanic slopes of Sicily. But in the early 19th century, a curious succession of events changed all that. John Tennant from St. Rollox and the Liverpool manufacturer James Muspratt joined forces in buying some sulphur mines in Sicily. The Neapolitans, then part of the Sicilian kingdom, became jealous, and a monopolistic agreement was signed in Sicily with a French company, and a high export duty was clamped upon the sulphur. Following a somewhat hair-raising exercise in gunboat diplomacy by Britain, the price of sulphur in this country was doubled, and manufacturers had to look elsewhere. An obvious solution lay in the minerals known as pyrites, where sulphur is combined with iron or copper or other metals. The one most commonly used was iron pyrites, or fool's gold. By 1870, 90% of Britain's sulphuric acid came from this source, much of it imported from Spain. Now it so happens that the Seaton Carew plant has never employed this raw material. What was used instead can be inferred by simply looking round us at the site. In years to come, an industrial archaeologist would find many a valuable clue in the multicoloured mineral heaps that are still visible. These black tips are the residues from the zinc smelting plant that once occupied the site. Zinc concentrates, rich in sulphur, were imported from Australia, and pure zinc was manufactured here. A byproduct was sulphur dioxide, and this explains the location of the lead chamber plant. But times changed again, and it became no longer economical to smelt zinc here, though the sulphuric acid works remained. Here is the most conspicuous heap on account of its golden brilliance. I was joined here by Mr. George Gilchrist, the works director.
Why was this material so much prized, Mr. Gilchrist?
Well, this material contains 99.5% sulphur, and in effect gives you a pure sulphur dioxide. So it gives you a pure acid and also gives you process control much better.
And is this the material you use here?
No, we use spent oxide here at the moment, although we do use small amounts of sulphur to dose it up to bring it up to the necessary percent sulphur in the raw material.
Yes, but if this sulphur is so pure and so good, why don't you use it throughout?
Cost, pure and simply cost. Chamber plants can burn anything that contains sulphur.
Yes.
Sulphur residues, spent oxide, anything else. We use sulphur to boost the raw materials up to a 50% so that we can actually work it on the furnaces.
So that instead of sulphur, you use this other material, spent oxide?
Yes.
Where did it come from?
From gasworks and anywhere where you've got coal gas purification, carbonisation of coal.
So it's a product of the purification process?
That's it.
What's it like to use it today?
Well, you have a lot of trouble with it because you get a lot of ferric oxide from it, and dust and one thing and another, so you've got to have the dust removed before it goes through the plant.
I see. Could you tell us something about this?
Well, we get impurities.
Yes.
We get impurities, we get iron oxide and other impurities going into the acid stream.
Sure. And the ferric oxide is the other main product you get?
That's right, as a byproduct.
Where does it go?
Well, we used to send it back to the gasworks for revivification.
Yes.
In fact, they used to purify gas for it, but just at the minute it's on the market.
So, in one way or another, different processes in the United Kingdom solved their problems of raw materials. Let me remind you, however, that the lead chamber process depends upon another material, the gaseous catalyst, nitrogen dioxide. This is expensive to make, and today nearly all of it has been removed from the effluent gas by an efficient process of washing. However, in the 19th century, vast amounts were lost into the air, wasting a precious resource and causing a severe problem of atmospheric pollution. In 1827, this pollution problem was solved by the French chemist Gay-Lussac. He devised a tower which was filled with coke. The function of these glass cylinders, or the coke in the real thing, is to provide a large surface area to enable the acid and the gas to come into close contact. The effluent gas from the lead chambers goes in at the bottom, and it meets a stream of fairly concentrated sulphuric acid running down from the top, which dissolves much of the oxides of nitrogen, and the effluent gas is therefore much purer. This has solved the problem of pollution, but it has meant that the acid which runs away from the bottom of the tower contains the expensively produced oxides of nitrogen, and this was very bad economics. This difficulty was overcome by John Glover in 1859. He devised another tower which now bears his name. It's the tower in the middle of the picture, between the furnace and the chambers. In this way, hot furnace gases pass in at the bottom of the tower. They sweep right up it and encounter the acid which runs down from the top. Now this is the acid which contains the dissolved oxides of nitrogen. And as it runs down the Glover tower, meeting the furnace gases going up, a reaction takes place and the nitrogen dioxide is expelled. So this catalyst that we call nitrogen dioxide is absorbed in the tower devised by Gay-Lussac and released and recycled into the chambers in the tower invented by Glover. The packing of the Glover tower turned out to be very important, as Mr. Fred Bryan explains.
This is the way we used to pack the tower for spent oxide. The idea of the 4-inch rings is to restrict the flow of gas going up too quick. Therefore, the acid coming down and the gas going up, it strengthens the acid. If it goes up too quick, the acid is not strong enough.
So the Glover tower, in fact, has this other function of concentrating the relatively weak acid from the lead chambers. This acid also is stored at the top of the Glover tower. And if it is allowed to run down, the ascending hot gases will drive off the water, so concentrating the acid as it flows from the top to the bottom. This then is the end product, 77% sulphuric acid running out of the Glover tower into the storage tanks. Let us take stock of the progress made. Gradually the problems of demand, construction, raw materials and pollution were solved, but one remained, the question of purity. The acid is usually brown due to iron oxide from the raw materials. It may also contain arsenic from the same source and a little dissolved lead. This makes it totally unsuitable for a whole range of uses. But most of all, it has 23% of water, as measured by its density. And removal of this by distillation is very costly in both fuel and time. This, in fact, remained a major problem. But none of these disadvantages was inherent in an alternative process which gradually replaced its older rival. This was known as the contact process, which dispenses with lead chambers altogether. Mr. Gilchrist explained why his company chose this method for their new sulphuric acid plant.
Plants are getting bigger and bigger and bigger.
Yes.
700 tons a day, 800 tons a day, and here we talk about 380 tons a week. I think that's the point.
Yes, but you wouldn't build another bigger lead chamber plant?
No. Initial capital cost would be too much. In fact, here we're talking about £300,000.
Yes.
When you could build a contact plant that would make twice as much as that for a lot less.
Yes. So we'll never see one like this again.
The 19th century alkali industry makes today's chemical industry look a model of cleanliness and safety. In those days, it was one of the filthiest, most dangerous activities in British industrial history. The next programme of this series traces the rise and fall of the industry and its replacement by more efficient processes. That's the alkali industry, and you can watch it on Saturday the 21st of April at the same time here on BBC Two. But right now, for the series Management in Post-Compulsory Education, we look at the new college system for the over-16s in the Sheffield area.